Let's recap category 5. So category 5 is one of our short categories. It's exponential functions, y equals ab to the x power. We're going to graph them. We're going to look at the domain and range. We're going to look at key features, including the a and b value and what do those represent. And we're going to look at exponential regressions. So category 5, exponential functions. So remember, exponential functions, they either started low and then they shot up really fast. And we called this a growth because reading from the left to the right, this is growing bigger. Or we called it a decay, where it started big and then came down and got low. And we called this a decay. Decreasing, growing, decreasing. We had something in exponential functions called the asymptote. Okay, asymptote has the letter y in it, and so the asymptote was y equal. The asymptote was not a very nice thing. It's the line that played the I'm not touching you game, and as this graph swooped in, it was getting really, really close to this line right here, but it never touched it. It got really, really, really close, but it never touches. It looks like it's touching here, but it's not. So the asymptote is the y, and it's y equals, a lot of time it's y equals 0. It's wherever this graph is. So let's say that this is -1, and let's say this is going like this, and it looks like this right here. So I would say this line is getting really, really close to -1 right here. So it's an asymptote, so it'd be y equals, and then I look to see what it's getting really close to. It's getting really close to -1. So whatever the value is it's getting really close to, that's the asymptote. You can always remember, don't make an asymptote out of yourself. Yeah, maybe if you think of it like that, then you'll remember what it is. Okay, arrows on the end. That means it goes forever and ever in both directions. So let's talk a little bit about domain and range. All right, domain is how wide is it? It's the x value. Well, if it's going forever and ever this way and forever and ever up and up and up, it's getting wider and wider and wider. There's no end to the values that it's going to be. So if there's no end, I would say it's all real numbers. Arrows are a giveaway. But I do notice on the range, how tall is it? I notice that there's no graph down here. The graph is right here and up. It's all up in here. It's not down in here. So if the graph is not down here, then that means it must have a boundary. So the bottom of it right here is at -1. The rest of the graph is all up this way. So I would say y, and am I looking at values -2, -3, -4 down here, or am I looking at values up here? Yeah, I'm looking up here, so that means I am greater than. Do I physically ever equal -1? No. I'm playing the I'm not touching you game, and I'm getting really close to -1. In fact, if I put this in my calculator, it would tell me -1. It's getting so close. But I never actually touch it. Okay, domain and range. Let's see. Let's do another one. We remember growing, we remember decaying, and we remember domain and range. Now let's look at those key features. Okay, so let's say I'm going to start here. I'm going to call this 100. Here we go. So would I say this is a growing or a decaying graph? I would say it's growing. Read from the left to the right, and it's getting bigger. I want to know, let's say it's growing by 20%. That's what it's growing by. I want to know, what is my y-intercept? Yeah, and you're probably already looking at it. Yeah, it'd be right here. This is the y-axis. Intercept is when do I intersect the y-axis. It's right here at 100. That is the y-intercept. It's also known as where my graph starts, or the starting amount. In our equation, y equals ab to the x power, the a was the y-intercept. It was also the starting amount. Starting amount was like if I bought a car and the car cost me $20,000, then my starting amount for my car, when I do y equals ab to the x power, my A value would be that 20,000. Okay, so in this particular scenario, I'm starting at 100 and I'm growing 20%. So here we go. So y equals, I'm starting at 100. But then you got to put that growth rate in there. You don't put 20%. So remember this is how I was explaining it the other day to my son. If I give you this eraser, you have 100% of that eraser. All of this eraser is you. Not 20% of it, not 80%. All of this eraser, it's yours, 100%. If I give you this pen, 100% of that pen is yours. Not 80%, not 10%, but 100% of this pen is yours. When I give you something, 100% of that's yours. Every time you have something in a situation like this, you always start with 100%. I can't start you with less than that. You have to start with 100%. Now, I'm either going to give you more, grow it, or we're going to decay it. In this case, I'm going to grow it by 20%. I take my initial 100 and I add 20% to it. 100 plus 20 is 120%. Problem is, you can't put percents into an equation. You have to change it to a decimal. So we move it over, and it's 1.20. So I'm going to come over here. What's my rate? 1.20. Okay, let's take another situation. Let's say that my starting amount is 20,000. It's a car. But the minute you drive it off the lot, oh my goodness, it decreases by 3.5% every year. So we're going to say decreases. Okay, decreases. Well, I always start with y equals ab to the x power. What's that starting amount again? It's 20,000. That part's easy. It's this rate in here that gets a little tricky. Okay, I go, here's my car, I buy it. I buy 100% of my car, right? 100% of my car. But when I drive it off the lot, it decreases by 3.5%. What is 100 minus 3.5? So I'm going to put it in here. 100 minus 3.5 is 96.5. Okay, so I'm going to come up here. This is where I'm working. 96.5%. Oh, but I can't put percents into here. So I have to move my decimal over, and it becomes 0.965. And there is my equation. Remember with these, when you're doing growth and decay, if you're bigger than 1, you're growing. If you're less than 1, you're decaying. Now, what do I mean by that? In my parentheses, if I see 1.13 to the x power, this would be a growth of 13%. The flip side of that is if I see 80.87 to the x power, that's less than 1. That means I'm decaying. I'm only growing 87% every year, which really means I'm not growing 100%. I'm decaying away. I'm decaying by 13%. So this is a 13% decay. This is a 13% growth. Okay, do you see the difference? When you're decaying, you're less than 1. This is less than 1. So I could do real quick. 1.12 would be a growth. 0.97 would be a decay because it's less than 1. 2.20 would be a growth. It's bigger than 1. 1/3. What would 1/3 be? Wouldn't that be 0.333? That would be a decay. So there's different ways I could ask it. Okay, so hopefully you kind of got that in your brain. Graphing exponential functions, we know A is the starting amount. We know that we can graph it from that. Let's see what else do we have. Domain and range, we did that. Wow, there's not a whole lot more to show you. So we did growth, we did decay. What? How many minutes? I'm at 9 minutes. Yeah, I think that's good. To do an exponential regression, things that you would do with a regression, bacteria would grow. If you have a problem involving bacteria, that would be an exponential regression. Other ones might be if something in a bank, if you're growing your money exponentially, that would be a regression. I'm trying to give you some like actual word problems. When you do your regression, it is going to be down here at 0. Okay, there it is, expo regression. So you know number 4. Oh dear, stat, calculate. You know number 4, right there. You know number 5, quadratics, and you know 0. So 0, 4, and 5 are going to be the ones that you use the most. Quadratic is going to be when you're throwing something off a bridge, kicking a ball. Linear is going to be like you're selling boxes of cookies, you're driving a car at a steady rate. Exponential, you're going to look for things like bacteria, things like that. All right, guys, thanks for watching. Good luck on your categories.